All right, this is the last section for chapter 12, and we're just going to cover two topics. One is going to be oxidation of alcohols using chromium reagents, and then the other will be Sharpless asymmetric epoxidation. So we are skipping, this is on the first page, but skip section 12.13 and section 12.14 on green chemistry and biological oxidations. You don't need to know that material. Okay, so oxidation of alcohols, there are two types of chromium reagents that you'll see: potassium dichromate with water, or PCC, which is pyridinium chlorochromate, and that's used in dichloromethane, no water present. Both of these react as chromic acid, CrO3, which is in the chromium +6 oxidation state. So primary alcohols with PCC are oxidized to aldehydes, and with potassium dichromate and water, they oxidize to carboxylic acids. Secondary alcohols, either reagent is going to convert them to ketones, and tertiary alcohols don't react. So the mechanism's on the next slide, but the mechanism requires removing a hydrogen from the alcohol carbon. So if I have a tertiary alcohol, there's no hydrogen on the carbon. So you can't oxidize a tertiary alcohol. Okay, so the mechanism involves formation of a chromate ester intermediate. So you start with the chromium reagent, and I've just written it out as CrO3, and you see a color change in these reactions. So this is bright orange, and I have just one propanol. The oxygen adds to the chromium, and you have a new bond between the oxygen and the chromium, and this is called a chromate ester. So a base then pulls off a hydrogen from the carbon that was the alcohol carbon. Those electrons go in to make a new pi bond, and you break the oxygen-chromium bond. This step is really an E2 elimination step. So you're pulling off the hydrogen, forming a pi bond, kicking out a leaving group, which is the chromium. So that gives an aldehyde. And if you're just using PCC, it stops at the aldehyde. And your byproduct is chromium +4. This actually gets reduced further to chromium +3, which is sort of a greenish color. And if you have water present, so with dichromate and water, your aldehyde forms a hydrate. And this is a chapter 18 reaction, so you'll learn that later on. But in the presence of water, the aldehyde partially exists as a hydrate. And then water acts as a base to remove the hydrogen after you form another chromate ester and form the pi bond, and now this OH of the carboxylic acid came from the water. So with PCC, there's no water present, so you can't go on to the acid stage, and it stops at the aldehyde. So some examples of this oxidation. I've got here a primary alcohol with PCC. So the product is going to be aldehyde. This one, I've got a secondary alcohol and a tertiary alcohol in the same molecule. Nothing's going to happen to the tertiary alcohol, but the secondary will be converted to a ketone. And then the third one, I have an allylic alcohol, dichromate, and water. And the carbon is going to become a carboxylic acid. And then the last one would be a synthesis, and if you are starting with an alkyl halide and you want to have a ketone in that position, first I'd have to convert that to an alcohol. So that would be an SN1 substitution on a secondary halide, and then I could use either PCC or dichromate to make the ketone. All right, so the very last topic is the Sharpless asymmetric epoxidation. So this is a useful reaction. It's enantioselective. So a lot of times in a synthesis, you want to make just one enantiomer instead of a racemic mixture. So this is predictable for allylic alcohols, and Barry Sharpless won a Nobel Prize for this reaction and related reactions back in 2001. So in this reaction, you've got a chiral component. So diethyl tartrate is a naturally occurring compound. It's part of what we call the chiral pool. And then you have a peroxide, T-butyl hydroperoxide, and a Lewis acid, titanium isopropoxide. So without going into what this looks like, these come together and form a complex. And the alcohol of the allylic alcohol helps to deliver the oxygen of the epoxide to just one side of the alkene instead of both sides. So to predict which product, you always have to draw the allylic alcohol a certain way. The alcohol in the upper right corner. I've got this on the next slide. And then if you use one enantiomer plus diethyl tartrate, the oxygen adds to the bottom. And the other enantiomer minus diethyl tartrate, again, these are both natural products that you can buy, the oxygen would add to the top. So this is the structures of diethyl tartrate down here at the bottom, and then T-butyl hydroperoxide. So this would be an example. So if I look at this allylic alcohol, allylic means that the alcohol is on the carbon next to the alkene. With MCPBA, I'm going to get two products, one-to-one racemic mixture, where the oxygen's on the top, the other one has the oxygen on the bottom. And if I look at this sort of from the side, this is the top face and the bottom face, right? So if I draw this so that the OH is in the upper right corner, then I can predict what's going to happen. So with this combination of reagents, so MCPBA, there's nothing chiral, and I'll get a racemic mixture. With T-butyl hydroperoxide, titanium isopropoxide, and minus diethyl tartrate, the oxygen's going to add to the top face, and I'll get only this enantiomer. And if I use the opposite tartrate, the opposite enantiomer plus diethyl tartrate, then I'm only going to get, again, just one epoxide forming out of the two possibilities, and this one's going to have the oxygen adding to the bottom face. So that is just a variation on epoxidation of alkenes, and it's one of the few. There are a number of enantioselective reactions in organic chemistry. This is just one of a few examples that you will learn. So that is where we're ending with chapter 12. And that is the end of 3010. So all of this is going to be covered on the final, comprehensive, and hopefully keep in mind that when you go on to 3020, all these things you learned in 3010, you're still going to need to know. So whether you take it in the summer or next fall or even next spring, you will have to go back and review all of these reactions, but for now, this is all we're going to cover.